Okay, let's continue from where we were. Are there any questions or issues you have with what we've discussed so far? Okay, so we talked in the last slide about the effect of the base field, if you like, on the overall structure of the wind and the structure of the IMF and the interplanetary region. And I mentioned that we observe magnetic fields in stars, in young active stars, that we see this concentration of magnetic field in the polar regions. Now, you probably want to know how can we observe magnetic fields in stars that are far away, especially when we already discussed that stars are kind of a point source of light, right? So how can you observe magnetic fields in other stars? And by the way, it's the same question, how can we observe magnetic fields on the sun, right? So again, the thing we can observe is the light. The light is an electromagnetic wave. It propagates this way, and it has kind of a calibrated magnetic fields and electric field that oscillate perpendicular to each other. So the electric field, which is the red one, oscillates this way, and the magnetic field oscillates in the horizontal direction, and they're both perpendicular. They oscillate perpendicular to the direction of the propagation of the wave, and that makes it what kind of wave? Transverse wave. Yeah, it's where the oscillation is in the perpendicular direction to the propagation direction. Okay, so every light, every photon that we measure represent an electromagnetic wave, and what we can do in the context of magnetic field is to look at the changes of these electric and magnetic perturbations of the wave as it passes through the medium. That can give us information about the medium. Why is that? If this wave propagates in vacuum, does it change? No, right? But most space is ionized, it's plasma, and this is most of the medium between us and the source of this wave. And plasma, because it's ionized, is responding to these electric and magnetic oscillations, and that will move the particles pretty much, it'll make them oscillate, and they will generate, this oscillation will generate some fields in response, and these fields in response will change the direction of these oscillations, their magnitude, etc. Okay? And this is what the most simple way to capture that effect is the plasma frequency. Once you start to talk about mixed plasma with different species, electrons, ions will do different things. But in general, the idea is that because this is an electromagnetic wave with electric fields and magnetic fields, and they passing through an ionized medium, there will be some electromagnetic interaction that will affect the particles, but also will affect the wave, and it will cause some kind of refraction if we're going to talk about pure wave analysis. So the wave gets into the medium in some direction, some properties, and it comes up with these properties slightly modified by the medium. That's what we call refraction. There's an index of refraction that can, in the case of plasma, can be directly related to the plasma oscillations of different kind, and it's a whole zoo of waves that we have in plasma that will affect this index of refraction. But in a very simplified matter, that's how it works. So what we can do, we can look at this light, this electromagnetic wave, and look in particular about the electric field and see if it's changed. We can get some information about the medium at which it's passing through. Okay? So the first way to look or try to observe magnetic fields is the Zeeman splitting. This is actually come from a different property. You remember we can break down the light that is coming to us to different wavelengths and to see spectral features like emission and absorption lines. Again, emission is when the flux is enhanced by a certain wavelength, and absorption line is where the flux is decreased by a certain wavelength. And again, it's associated with certain molecules that exist in the medium. Okay? The Zeeman splitting is an effect that tells us that a single line, which is represented, say, here, can be broken down into 3 different lines when we have magnetic field in the neighborhood. Okay? So magnetic field, because it changes the internal quantum states or quantum energy levels of a state, that energy will be broken down into 3 or more different levels located around this unmagnetized state. Okay? And depending on the strength of the field, these split lines will be further away. So if we know that we should have this line, but we see this line splitted like that, that should give us information about the magnetic field, and there's actually a relation between the level of splitting and the magnitude of the field. And this is Zeeman splitting, and this is how we can measure magnetic fields in stars and the sun. The problem is that in stars, we need to be able to distinguish between this splitting around this line. You remember we have this problem of resolution of the spectra. If, say, we look at this line and we don't have enough resolution to say if it's one line or it's a split line, then we can't say anything about the magnetic field. We don't have enough resolution to do that. In an extremely sensitive cases and maybe extremely strong fields, we will be able to see some splitting in a certain line. And this is a unique case when we can actually measure the magnetic field in stars. But these are really unique cases. Okay? We can't do it for the sun because it's much closer to us, or our resolution, the necessary resolution to being able to notice this splitting is lower. And this is the older instruments that used to measure the magnetic field. I believe the Wilcox Solar Observatory still use Zeeman splitting as the method to observe the magnetic field of the sun. Okay, so we can use Zeeman splitting. This is one method. The other way is what we call light polarization. The light polarization is the change in the direction of the electric field perturbation in the electromagnetic wave as a result of passing through a medium, due to the things we just discussed before, the interaction with the medium and the electromagnetic interaction with the medium. There are a number of Stokes components that define the polarization. In general, we have the Q and U components. So imagine that the wave is coming out of the board, and this is the plane of the electric and magnetic field, this X and Y component. So the fields oscillate like that or like that in this plane, and the wave is moving towards you. Okay? And towards you, this is the line of sight. That's where you observe it. Okay? Somewhere there, that's your telescope. Okay? A change in the direction of the oscillation of the electric field will tell us something about the polarization, the linear polarization. So it's the change in this plane. And the field can also rotate counterclockwise or clockwise, right or left, around this direction of propagation. Okay? And this is the V Stokes component. And one of them gives us information about the magnetic field in this direction, along the line of sight. And the other one gives us information about the magnetic field in this plane. Okay, so if we measure these components, the linear and circular polarization of the electric field, we can get some information about the magnetic field that exists in that medium. Okay? Now, what can lead to a right or left polarization? Can you think about something that is related to the electromagnetic force that in one case moving in one direction and the other one moves in the other direction? What property in electromagnetism can have plus or minus sign? Charge, okay? So what can lead to this right or left polarization? The interaction with negative or positive charges, right? In other words, electrons and ions. So I think, as far as I remember, the left polarization gives us information about the electrons in the medium. The right polarization gives us information about the ions in the medium. But that doesn't important. The important thing is that looking at light polarization, we can get information about the magnetic field in this plane and perpendicular to the plane in the direction of the line of sight. Okay? So this is a method that people are using to construct maps, magnetic maps of stars that are far away. And this animation shows, this is what we're actually looking is not the Stokes components themselves, but some ratios of the different Stokes components of the light polarization. Assuming we have a radial field concentrated here in a magnetic spot, this is the signal of that ratio, that specific ratio. You can see it as this spot passing in front of us or in the line of sight direction. You can see how the signal changes. This is a different ratio, and this is the third ratio. And what people do, they take this observed polarization behaviors, and they make a fit to certain polarization patterns that are empirical, analytical, and from that they can construct this kind of spot pattern on the star. And this is how they construct these magnetic maps on the stars. These are, of course, very low resolution. There's a lot of uncertainty in this method. It's called the Zeeman Doppler imaging technique, or ZDI. Again, it's a combination of measuring the Zeeman splitting and the Doppler imaging through these Stokes components. Just a second. And it enables to construct some low-resolution maps of the magnetic fields of stars. One thing we need to do to have in this method is that the stars needs to rotate really fast. So these features coming over and over again, coming back over and over again. So we can stack the observations on top of each other and get low signal to low, noise ratio. That is enough so we can say, okay, this is what we actually have there. With one observation, we don't have enough certainty in the observation to state that this is what we see. We need to repeat the observation many times, so then the certainty of the observation is sufficient. Yeah, question?
So, I mean, you sort of keep that this, patterns are really uncertain but if you have a simple light curve, how can you get latitude longitudinal distribution?
It's a good question. So in the real maps, they don't have a single one. They have a number of spots. And they just feed it to many, many models of, say we have a spot here, here, and here, how the signal look like. Then they moved it around. They have this algorithm that kind of optimize the particular mapping to the signal they have, and that's the best fit, pretty much. So that's how they do it. This method is highly criticized by many people in the astronomy community. So, but on the other hand, this is the only technique that provides some information about not only the magnetic field itself, but its spatial distribution. Yeah, question? Could because you have the polarization pattern is changed due to the fact that you have this strong localized magnetic field here. Well, it's a combination of both. again, it's fitting to many, many different potential cases that could match it. Another question? Okay. So that's how we measure stars, magnetic fields in stars. Okay? And a lot of the information I give and I will give is based on this mapping technique. Let's talk about CMEs. I know you probably heard about them. It's these giant explosions from the sun. We know that other stars have CMEs also, or we actually don't. We know that they have some, we observe some artifacts of CMEs, and we're going to talk about this relation later. A typical CME on the sun throws about a Mount Everest of material into space. In terms of energy, it's a very strong earthquake. And typical speeds are within this range of 500 to 1,500 kilometers per second. Takes the typical CME about 2 to 4 days to reach the Earth. Okay. Now, CMEs also take mass from the sun, and this will be this is something to remember for later. Okay. So the question is, how do CMEs change with stellar evolution and change in activity level? So far we talked about the so-called ambient state. The ambient solar wind, the ambient magnetic field, it varies within cycle time scales, but it's still kind of ambient. CMEs are the transient state of the transient state of the star. It's kind of a local short explosion that is very notable, but it's not part of the ambient state. Okay, and we need to think how CMEs change and their behavior change with different stellar types. Okay, and I would like to make a side note that many of the things I will talk about from here, and also things that I already talked about, it's a semi-open question. There's not enough data to say too much or distinguish between specific models. But I just want to give you to raise the questions, and so you can think about these things and maybe come up with the solution sometimes in the future. I went backwards. That's the wrong direction. Okay. So when we talk about CMEs, we need to look at certain aspects. So if we talk about different stars, what is the impact of the CME initiation itself? CME initiation is still an ongoing semi-open science question in the sun. And the question is how when we move across different spectral types, what will be effect on the initiation itself? And then what's the effect on the propagation and evolution of the CMEs when they already launch out? Okay, so we can distinguish between these two. What observations we have about CMEs in stars? We have stellar flares. That's the only thing we have. The only indication that we do have this explosive-like processes on other stars. We can't observe CMEs. It's a field of research that is at a high priority right now by many groups, but nobody figured out yet how to do that. Okay, so let's talk about the impact of CME initiation. So as we discussed, in young, fast-rotating, active stars, and by saying active, it means that they flare a lot. That's one of the indications what we mean by saying active. So there are two things that make a star more active. Its X-ray and UV luminosities will be higher than less active stars, and that represents the overall activity on the star in terms of active regions, magnetic spots, etc., that typically increase the level of X-ray and UV. Also, these stars seem to flare a lot. They have high frequency of flaring, and therefore they're active, right? That's the terminology. So what's the impact of CME initiation if most of the concentration of the magnetic fields or active region is in the polar region? Think about it. In the case of the sun, the active regions are located close to the equator, at about 30 degrees or less from the equator. So most CMEs will be launched close to the equatorial plane, where a planet can reside, for example. So if we think about the impact of CMEs on a planet, and the planet resides on the equatorial plane, do the CME will go here, or because of the high latitudinal appearance of the active regions, all the CMEs will go to high latitudes, and they won't really affect that planet, right? So that's one thing to think about it. And we know that the CMEs pretty much originating from active region in the sun. So there's reasonable reason to believe that the same thing happens in these kind of stars. And the other question we can ask is, do the CMEs scale with the overall activity and magnetic field strength, right? Say we have a star that we know that has a magnetic field that is much stronger than the sun, an overall field. And we do see M-dwarf stars with kilogauss fields sometimes. And these are not small active regions. We see these kilogauss fields extending significant amount of the stellar surface, based on ZDI maps that are still might be iffy. But I think we have a pretty good idea that the magnetic fields of M-dwarfs can be much stronger than the sun, than G-type stars, like the sun. Now the question is, if we boost the field, the overall field, which is these red lines, a lot, do the CMEs and the active regions scale accordingly? Or do the active regions still appear in the same kind of size and magnitude of magnetic field as in the sun, even though the overall field is much stronger? And this is a good question for dynamo modelers, or in the context of dynamo action in stars, because it's a good question. It's one thing if we show that the CMEs and the active regions scale with the overall field, or if they're not scaled, then we need to explain it in terms of how the dynamo action works, right? So that's the other thing we need to think about it. And again, this is an open question. Now let's talk about in the context of, okay. And we can think about different initiation mechanisms for CMEs. The conventional solar CME model is the so-called slinky model. We have a flux tube that is being twisted by some kind of motions on the foot points, surface motions, that stores energy in the flux rope, magnetic energy. Then we have a sudden release by means of reconnection or some other magical way, right? So it's like twisting the slinky and then maybe cut it in the middle, or a rubber band, cut it in the middle, all this energy is released. But the idea is we have a relatively slow storage of the energy, which is magnetic, and then a fast release of that energy. That's the conventional model. Now, we can think about an alternative mechanisms. For example, this is a simulation I did of an FK Comea star. This is a giant K-type star with 2 days rotation, so very fast rotation. And you can think about that instead of twisting the flux tube, you have this magnetic loop that as a result of the fast rotation is being stretched in the azimuthal direction. So we also store the energy. Imagine just stretch a rubber band as a result of the centrifugal forces. And then you have the same sudden release of the energy. You can still get a CME, but this mechanism is different. And there are some other alternative similar mechanisms that we can think of. Okay, so the question of the initiation itself might vary between other stars or stars that are different than the sun and the solar CME view that we have. Now let's talk about the propagation and evolution of CMEs with respect to different types of stars. Again, we can talk about stars that rotate very fast. So the Parker spiral is really condensed or compressed around, even within the corona. So not only we have this stronger overall overlying field because of this azimuthal stretching, also this leads to a higher density in the corona. And so the ambient force, or if you like, the ambient medium that the CME needs to go through as it comes out, it's much more dense. The magnetic pressure is higher of the overlying field. And we can ask, what's the impact of such thing? Also, the field might be very strong in these stars. So the overlying field is stronger. It's stretched around. The density is higher. It's harder for the CME to go out. And this is a toy simulation I did for the same AB Dor star I showed you before. This is a CME, and you can see that it's kind of, I think I'm going to make it out, right? And if we use the same simulation in the case of solar field, this whole thing will just going to blow up. So a stronger overlying field will make it harder for the CMEs to make it out. And that can have consequences. And this is an extremely recent paper. It was pretty much published yesterday at EPJ by Julian Alvarado Gomez. He did a series of simulations using the Batsaras code where he took a solar real CME event. And what he did, he boosted, for different cases, the overlying field. So he started with a solar-like field, which is about 10 Gauss dipole field, if you like. And he went all the way up to 75 Gauss field. So it's not that strong stellar field in the context of these M-dwarf stars. These M-dwarf stars have a kilogauss field sometimes. So only boosting by maybe 7 times higher field of the dipole component of the star, the CME couldn't make it out. So this plot shows you the kinetic energy of the CME as a function of the polarization flux of the star. This is the magnitude of the field, of the stellar field, the overlying field. So this is a weaker field, this is a stronger field, and this is kinetic energy that goes to the CME. And these circles represent the region where the CME was able to make it out. Okay? And you can see that in order to make it out for this higher field, it had to have much higher kinetic energy. Otherwise, it wouldn't make it. But at some point, when the field became too strong, all these points here were failed CME. The CME didn't make it out. Now, what will happen to all this energy? Okay, the flux loop has a lot of initial energy that was stored. We do have a release of that energy. The CME is trying to gain the kinetic energy going out. It can't make it. Where does this energy could go to? Any ideas? We have energy going to the corona. Goes to the particles of the corona. When we give, what? Kind of. So the energy will go to the particles. They can be accelerated, heated, go down. All this energy will be deposited in terms of temperature increase, if you like. That temperature increase will be manifested in emissions. And we're going to talk about this towards the end in context of flare. So it will go to the flare component of the CME. Okay? So we know that most CMEs on the sun are associated with flare. These are the excess of energy that hits the flanks of the CME, if you like. In a typical CME, most of the energy will go to kinetic energy of the CME. But if that energy cannot go there, it will all go to the flare. So the result of this failed CME would be manifested in an extremely, extremely energetic flares. And we actually see these so-called super flares in other stars. And this work pretty much demonstrated that the origin of these super flares, these high energetic flares, can be the result of a failed CME in the case where the overlying field of a star is much, much higher than the sun. Okay? So this is the possible effect on CMEs when we go to different stars. So that's where I finish my first part of the lecture, pretty much overviewing the standard features that dictate how the heliosphere look like and how the solar corona and the solar wind look like, and what's the possible effect if we change the parameters of the stars. Okay? So are there any questions about this part before we move on to the next part. Okay. Take a sip of water and we continue. Okay. So in this part, I'll move to talk more about specific problems in astrophysics that the heliophysics processes that I just reviewed may be important for. Okay? They are different than heliophysics. They deal more in an evolutionary time scale of stars, pretty much trying to understand not the snapshot in time that we have for the sun, but the overall behavior of a star and its astrospheres and winds and corona over time. Okay? So, stellar evolutions and magnetized winds. So, one thing we know from many observations on stars, and again, most of what we talk here is in the context of solar analogs, low-mass stars, cool stars with hot corona, not giant, massive stars that are really bright and they don't have hot corona. Okay? So we know that there is a clear relation between rotation, age, stellar activity, and magnetic field. And there are a number of empirical relations that kind of scaling laws that relate these parameters together. And the overall view is that stars are born, and when they're young, the rotation is really fast because at the beginning they have an accretion disk around them. Then that accretion disk is gone, and the planets are the only thing that is left. And through that process, due to angular momentum conservation processes, when the disk is gone, the star is spun up to faster rotation. So young stars with no disk at the very initial stage of their life are fast rotators. And as a result, we also see that the magnetic field seems to be more strong. We see more magnetic fields in general. And what that means is kind of a vague definition. It's manifested mostly in terms of the stellar activity that we can actually observe. And this is, again, the total X-ray and UV flux. That's the flux that comes from the hot corona. And we see more of that if we have more active regions. That's what we see in the sun. During solar maximum, the X-ray flux goes up. So we assume that these stars are more active in the same manner. Their magnetic fields are stronger, they have more spots covering their surface, etc. Okay? So young active stars are very active. They're like teenagers, you know, they have interesting life, right? And they get older, life gets boring and more boring and boring. And then they spin down, they lose angular momentum, and then they just become old stars that do nothing but to watch news on CNN or something like that. Yes, I'll get that there. I'm kind of in the mid-age crisis, I guess, when I try to catch up with my kids that drain all the energy from me, and I lose angular momentum as a result. Okay. So these plots pretty much show what I just talked about. There's a clear relation between the age and rotation rate. The rotation rate is high at the upper parts and low here. This is the age from young to old. This is the sun here. This is a plot from Tom Ayres' paper. There's actually a typo in this plot because the sun is viewed as less than 1 billion years old when it's obviously 5 years old. But I think the plot is correct otherwise. But the idea is that we see a clear evidence that stars or main sequence stars or low-mass stars spin down as they get older. Okay? So the sun is about 5 billion year old, pretty much standard G stars, and it has a rotation of about 30 days. We see older stars with about 100 days rotation period. We see very young stars with even less than 1 day rotation period. They rotate really, really fast. This plot here shows the activity level as a function of, this is rotation, but rotation can be associated with h, so we can relate everything together. It shows the, pretty much the X-ray flux as a function of rotation. This is actually the Rossby number, which is the rotation normalized to the convection turnover time. It's the time that it takes for stuff to go from the top to the bottom of the convection zone and up, or maybe only halfway. It's kind of the azimuthal motion divided by the vertical mixing motion, if you like. It's another indication. It's another way to plot it. But what I would like you to take from this plot is that this is rotation. So this is slow rotation on the right, fast rotation on the left. And this is X-ray luminosity. You can see that the X-ray luminosity goes up as we boost the rotation up. And it gets saturated at this point, which is about the 2 days rotation period mark. And this is also a semi-open question, why we get this saturation. Dynamo processes. This is the magical word to explain all this kind of stuff. For me, the view is that dynamo process means that we don't fully understand it, because we don't understand dynamos. There's not a single dynamo model that can, and I'm quoting Ben Brown, who is here at CU. He's probably one of the most prominent dynamo physics people in the world, worked both on the sun and on stars. And he told me, I get reversals, I get all these beautiful features that I would like my model to get. And he has the most sophisticated dynamo model in the world. And he stated that despite of the fact that I get all these features, I can't explain why they are, why they're so. Why we get these features, why we these specific time scales, these particular length scales, etc. So dynamo models, even the more successful ones, don't provide a lot of physical well, they do, but in a very simplified manner. And this is because, again, dynamo is the same as the corona. It's a very complicated problem. My guess is that we probably simply don't have enough computing power to properly solve the equations of the dynamo process. And once we hit that mark, I'm sure we're going to understand much better how it works. But because the generation of this activity is associated with the magnetic field, this saturation is associated with something that happens to the magnetic field as you mark the two-day period rotation. But there's no full theory that really explains why is it so. It's an empirical observation. Okay? In terms of the rotation-edge relation, there's this scaling law of ACE versus rotation was introduced by Skumenich in 1962, I believe. I think he always was working in this building, was at AJO, or CU, one of them. It pretty much states that the rotation scales with the life of the star to the power of 1/2, the square root of the lifetime of the star. I think this is in giga years. Okay, and it's a scaling law that we see that works pretty well for main sequence stars. But we need to need a mechanism to explain why stars spin down with h. So they lose angular momentum somehow, and we need to come up with an explanation. How is it so? So the dominant explanation, and it's kind of an old but still valid explanation, is that the concept of magnetic braking. And it's as the result of the magnetized stellar wind that these stars have. And this is how it works. We have a star here in the middle. We have the alpha, and we have a wind, stellar wind that is magnetized and is flying out from the star, flowing out from the star. And this red circle represents the Alphen surface, which is the collection of the Alphen point at which the field lines are breaking up and open up to the interplanetary medium by the wind. Okay? Now the idea is that as long as the field lines are closed within that surface, there's a conservation of angular momentum, because the whole thing co-rotates. Once the wind passes that point, the field line is breaking. There's no more angle. There's no conservation of angular momentum anymore. And the mass that, or the parcel of mass that just passed this surface, it's pretty much lost to space. It won't come back. Now, we can calculate the total angular momentum loss over this sphere by integrate the total mass, or process of masses, if you like, that is lost, and the amount of angular momentum that each parcel will have and will take with it. Okay? And in Weber, in 1967, Weber and Davis were, I think, also here, came up with this idea of magnetic braking. If you assume the star is a dipole, the stellar magnetic field is a dipole, we have a radial outgoing wind, and we also have a spherical Alfvén surface. They came up with this formula that the rate of angular momentum loss is dependent of the stellar rotation rate, the total mass loss rate that passes through that surface, and the distance to the Alfvén surface, the radial distance. Okay? So the takeaway thing from this formula is that if we define the total mass loss rate that is taken out by the wind, we can define the angular momentum loss rate, this J dot, and we can take that parameter and stick it in stellar evolution models so we can calculate the spin down of stars over time. Okay? So that's the concept of the magnetic braking. And you can reformulate that shows that if you calculate the rate, the spin down rate, this is the change in the rotation rate with time, omega dot, and normalize it to the current omega, you can see it depends on, again, this m dot. So this m dot is a key parameter to define in order to calculate the spin down rate and to use that in stellar evolution models. That's what this pretty much, this paragraph states. This is just an example of stellar evolution models. Just a second. This is a model by Bouvier, recent paper where we calculated the spin down of stars depending on initial mass and initial rotation periods. And you can see that there are different passes, but eventually they all collapse to the Skumanich law right here. Okay, so the Skumanich law seems to well capture the rotation periods of stars in the main sequence phase, but there are different passes that you can take to get there, depending on your initial mass, initial rotation period, etc. And then if we take this spin down, or this J dot, and stick it in stellar evolution models, they can tell us the different path of stars over their age across the HR diagram. So we can really track a star with a given set of initial parameters and see what will be the exact track of that star on the HR diagram. Question? Can you? Yeah, that's a problem. That's an issue. I'll talk about it. Okay. This mass loss rate is also important. This is pretty much a side note. In the context of the faint young sun paradox, how many of you have heard about the faint young sun paradox? Not including teachers and faculty. Okay, so here it goes. It was actually, so the faint young sun paradox was introduced by 1972 by Carl Sagan and Mullen, who was a co-author on this paper. It's pretty much the paper that started the whole concept of greenhouse gases and global warming. It started from that concept. So when the sun was young, it was about 30% more luminous. Less luminous, sorry. The luminosity goes with age. So it was about 30% less luminous. And if you calculate the irradiance at the Earth and the surface temperature of the Earth during the young sun time, the temperature was supposed to be below freezing. But there's a geological evidence that the temperature was actually above freezing. So you need to come up with some mechanism that the surface temperature on the Earth at that time was higher. That's the paradox. Okay? And one of the mechanisms to explain higher temperature is through the idea of greenhouse gases. So that's how it came to be. So this is what I state here. Another alternative mechanism is that if the sun was about 10% more massive at the young stage, and it lost mass at a very high rate that will end in the current mass, then the luminosity would be not as low as we thought. It would be actually higher, and the temperature on the Earth's surface would be higher. So then there's no paradox. Okay? So a 10% more massive young sun can be an explanation for the paradox, but you need to demonstrate that the young sun lost mass at a very high mass loss, a very high rate. Okay? So that's the context of what I'm going to talk about here. Now, can we observe winds of cool stars? Not really. The answer is kind of, I put it there. But the essence of this whole problem is that we cannot really observe directly stellar winds of cool low-mass stars because they're just too weak to observe. There's no signal that is strong enough that is generated by the winds that we can actually observe. When the winds are really powerful, like massive stars winds, they're strong enough to generate signals that are strong enough that we can actually observe them, especially when they collide with each other. They generate some shock features that we can actually observe. But in cool stars, we can't really see anything. So the reason I put kind of is that there is a recent method that was introduced by Brian Wood and Jeff Linsky to indirectly measure the mass loss rates and the winds of cool stars. So let me just go through it in details. This diagram shows the edge of our own heliosphere. You can guess it by noting the Voyager spacecraft here. So the solar wind flowing out, the interstellar medium coming from here, and they collide. And there's this interaction region that we also mentioned that there are two shocks there. And in one of them, we can build a neutral hydrogen wall as a result of the interaction between the two. There's an interaction of ionization and neutralization of particles through the process. So think about ionized stellar wind particles that hit maybe ionized hydrogen particles from the ISM. There might be some charge exchange. So the hydrogen can be neutral, but it's a very high energy neutral atom. Okay? So we have a kind of a region with a large density of high energy neutral hydrogen that we can actually observe. The IBEX mission that tried to produce a kind of a global view of the heliosphere pretty much look at the emissions from these hydrogen atoms. It's called ENA, energetic neutral atoms. Okay? So this is a signal that we can see from our own heliosphere. And if we have a Lyman alpha photons that go through this hydrogen, it will have a distinct signature eventually when it reaches our telescope somewhere here. Okay? Now, we know from observations that other stars definitely should have astrospheres. This view of our own heliosphere is actually seen in some few pictures of other stars. You can see this picture here. There's a clear shock in front of the heliopause, or in front of the heliosphere of that star, the astrosphere. There's another one here. So you can see there's a kind of a spherical shape around, but there's also kind of a more compressed region that is brighter because it's more compressed. There's also here, this is a zoom, and you can clearly see also the shock here. So we know other stars should have astrospheres. Now, the methods goes as follows. We sit here in the middle of the sun, according to this diagram, right? And that's where our telescope is. And this is the star that emits Lyman alpha photon. The Lyman alpha photon goes through its own astrosphere here. Then it goes through the interstellar medium here. Then it crosses our heliosphere, or heliopause. Then it reaches us. Okay? So let's see what will happen to the emission pattern of that Lyman alpha signal. So this is the original signal that this Lyman alpha line will have. This is a typical shape. It has this double bump shape. We know about that. Let's just put it this way. Okay? So we know that this is how the original signal or emission should look like. Now, as it passes here through its own astrosphere, that signal will have this kind of change in the middle as a result of this passage here. Then it will go through the interstellar medium, so most of this emission line will be blocked by the interstellar medium material, which is mostly hydrogen. Okay? So all this middle part of the signal is gone. And you can see, by the way, that this is a diffuse line. Emission line should be a line, right? It should be like that. But in reality, because of the constraints we have on the telescope resolution, in addition to the fact that this line comes through some kind of medium, in reality what we see is a diffuse lines. And if they're too diffuse, it means that we can't really say it's the line or not. So we need to have a diffused line pattern, but that is still centered around specific wavelength, so we can say this is indeed a Lyman alpha line. Okay? So now the ISM truncate most of the middle of the line. And eventually, there's this passage here through our heliopause that will create this part here. So eventually, this is the kind of signal we see, and this is the original line. Now, assuming that we know very well how the line will be changed as it passes through our own heliopause, because we're close by, we have a lot of information about that. We can run different models to find the best fit that will tell us something about this heliopause here. Okay? And the information will pretty much tell us how does this hydrogen wall look like in this heliopause of the star. Okay, so it's a combination of rather hard observation to make to start with, and these observations are done using the Hubble Space Telescope, by the way. But it's a hard observation to start with. Then there's a whole bunch of analysis and fitting to a different model to get or to assume which kind of hydrogen wall actually creates this pattern. And then finally, did I forget anything? Yeah, okay, there was this one. And finally, let me, okay. I used to have another, okay, let's skip there. And finally, this work assumes that they know what the ISM parameters are. They assume they know what density and velocity the ISM have that pushes from this side. And if they know, they assume they know how the hydrogen will look like, that will give us the parameters of the density and velocity from the other side, which is the solar wind or stellar wind parameters. This is the mass flux. Mass flux is rho times u. So it's just a dynamic pressure balance situation. Okay? There's one thing that is pushed from this side. This is the ISM. This is assumed to be known. From the signal, they deduct what's the boundary look like. And from the combination of the two, they deduct what the mass flux from the other side, meaning that's the mass flux of the stellar wind is. And that's the mass loss rate. It's the same thing. Okay? But you can see there's a lot of assumptions going in here, a lot of modeling fitting, and also a hard signal to start with. But still, this is an observation of the stellar mass loss rates. And this is a bunch of specific systems that they apply this modeling for, or applying this observation and modeling for. Another thing to note is that we can only do it for very close stars, meaning this kind of the stellar neighborhood stars. So you can see this is the sun in the middle. All these stars are within 20 light years away from us. These are our neighbors, right? This is the nice one. This is the not nice one. No, just kidding. You can see that these are the 4 out of the 6. You can actually see where they are. So this is the sun. This is 61 Cygni. Alpha Centauri, which is our nearest neighbor. Actually, it's Proxima Centauri, which is it's a triple system. So Proxima is the closest one, but Alpha Centauri is very close too, about 4 light years away. This is Alpha Centauri. Epsilon Eridani, it's a very close neighbor that is the center of a lot of attention because we think it has an exoplanet, a Jupiter-sized exoplanet residing at about 1 AU from the star. So it's the center of a lot of investigations, and it's our neighbor. It's another reason an epsilon in. But the bottom line is that we can only do this observation for very close stars. If they're further away, we don't have enough flux to get to the telescope so we can deduct this information. And what Wood et al. Did is that they gathered all this information to the format of mass flux of the stellar wind, or the star, as a function of the X-ray luminosity, because we do have information about the X-ray luminosity of these stars. And again, we can relate age, activity, rotation rate, and magnetic fields with each other. So using these scaling laws, you can relate these observed mass loss rates as a function of the X-ray flux. And these are the points that they have in the plot from 2014. You can see there are a number of plots that are out of this plot. This is Epsilon Eridani. You can see that it has a very high mass loss rates, about 100 times the solar one, which is here. But we also have EV-LAC, for example, which is an extremely active M dwarf. But it actually seemed to have not that high mass loss rate. So there's a perception in astrophysics in this context that higher activity, higher magnetic fields will result in more powerful winds, higher mass loss rates of the winds. But in a matter of fact, we start to see evidence that this scaling law breaks down at some point in terms of how active the stars are. And very active stars show some evidence that they actually don't have such a high mass loss rate. Okay? Now, Brian Wood and colleagues are trying to submit a proposal. They actually have approved HST observations to do more observations and pretty much fill this plot with more data points so we can have a better constraint on this scaling law. I did some simulation in this context, and what my colleagues and myself found, and also some other groups, is that actually it seems like this scaling law might be more moderate. So it should be more like that. So a very extreme mass loss rates of solar analogs doesn't seem to be more than 10 times the solar mass loss rate, but it's still work in progress. And again, the main problem is that we can't really constrain the results of our model. Even if we get good agreement, I did a simulation of EV-LAC. I got pretty good agreement with the value of mass loss rate that they obtained, but I have no idea. I have no way to say whether it's constructive or not, because it's an indirect measurement of the wind, and there's a lot of uncertainties going on there. Okay, so this is the range of mass loss rates that we seems to have from solar analogs, and the solar wind mass loss rate, again, can be obtained by just taking typical solar wind parameters at 1 AU, which is 5 cubic centimeters and maybe 500 kilometers per second. if you integrated that over a sphere of 1 AU radius, this is the number you get. I had a paper from 2011 when I looked at in situ measurements of the solar wind mass loss rate from pretty much every available spacecraft. And guess what? If you average the mass loss rate over about a day, maybe 3 days, you get exactly that number. Okay? And the mass loss rate of the sun seems to be very, very steady. And with this kind of fixed value. Okay? Now, we mentioned that CMEs can take mass from the sun as well. Okay? So let's try to estimate what is the amount of mass that CMEs take. So a typical CME will carry about 10 to the 13 to 10 to the 17 grams of material. And over the solar cycle, we have CMEs maybe every half a day in high activity level, and maybe once every 4 days during solar minimum. So if we take the average, we're talking about 2 to 3 CMEs per day, maybe. Okay, so that's the frequencies of CMEs. So if we take this amount of mass and the frequency of CMEs, and we calculate the kind of integrated mass that is taking from the sun by CMEs per year, which is this line here, we get a number of about 2 to 3, 10 to the 10 grams per second. That translates to about pretty much few percent of the ambient mass loss rate that the stellar wind is taking. So CMEs on the sun and mass loss rates of CME in the sun doesn't matter. That's the bottom line. Now the question is, when we get to these really, really active stars, we know that the frequency of flares and potentially CMEs can be much higher than what we have on the sun. Can be even orders of magnitude higher. Okay? So the question is, can the CMEs or the CME mass loss rate be so high to some level that it will take over the ambient mass loss rate and be the dominant mechanism for the star to lose mass? Okay? So this is the question we try to address. So this is what we find for the sun. It's just few percent of the solar wind. So what is the CME rate is much higher. And the question is how to scale the CMEs to other stars. So this work was done by a number of authors. Alicia Arnio, she's at CU now as well, published this in 2012. Jeremy Drake and colleagues from CFA also published it at about the same time. It was very nice because the two works were done simultaneously and the conclusion was pretty much the same. So it was kind of nice parallel scientific work on the same thing. So what we want to look at is that in stars we can see CMEs, but what we can see is flares. Okay? So we can look at the sun and try to derive a relation between the flare flux and CME flux, mass, kinetic energy, CME properties. Okay? So we want to come up with some scaling law of the CME properties as a function of the flare activity, and then look at the activity on other stars, which is the flare activity. This is the only thing we can observe. And then we should be able to estimate what is the CME activity and the amount of CME mass that is taken from the sun, from the star. And it's based on, these scaling laws are based on Yashirov and Gopal-Swamy work from 2009. Okay. So this is kind of the scaling relation. You can see that it scales the flare flux with the CME flux with some parameters. This is kind of the best fit. Oops, I went backwards. Okay, and this is from Jeremy Drake's works. It pretty much shows the mass loss rates as a result of CMEs as a function of the power law index that relates the occurrence of flares and the CMEs. Okay, so this is kind of the function that is relating the two. And you can see that the mass loss rates are very high. Let me just push two more. Yeah, so Drake et al. Obtained mass loss rates that are between 10 to the minus 11 and 10 to the minus 10 solar mass per year. is really high, 1,000 to 10,000 times the solar value. And similar values were obtained by Arnio. And just to make the point that this value here, if you take this energy, or the energy involved, it's about 1% of the total volumetric energy of the sun. It's just really, really high. Okay? And both papers pretty much concluded that these mass loss rates are probably too high, and that the extrapolation of the flare-CME relation probably breaks down at some point. It doesn't work anymore. You can extrapolate it up to a certain level of flaring activity, but if you go beyond a certain level, that relation is probably no longer valid. That's the conclusion of both papers. One thing I forgot to mention when I talked about this, the magnetic braiding concept, another way to look at that is that think about a magnetic field lines that is attached to the sun or the star in one end, and it extends to space as it being dragged by the stellar wind outwards. Okay? So below the alpha point, this field line co-rotates and conserves angular momentum. But as you go back, or you go beyond the alpha surface, this field line is being held somewhere at infinity, and it applies torque on the star. Think about it. You have a spinning wheel, and it's attached to a rope that you move far away from you stand far away, you hold a rope, and if you apply a torque on the rope, or you hold a rope, this will apply torque on the spinning wheel, and it will slow it down. That's what these magnetic fields do, pretty much. So another way to look at this magnetic braking concept is as these field lines that extend to infinity, they apply torque on the star, and they slow it down. It takes angular momentum from it. And the biggest effect is in the equator. If you're at the pole, the star spins like that. You hold the rope right here. It doesn't matter, right? So as you go towards the higher latitudes, the spin down is weaker. And the spin down is maximized near the equator. So one of the things Alicia Arnio did in her paper is she related this torque factor to this mass loss rates of CMEs parameter here. Now, another thing to think about this effect in the context of the Feng-Tian sun paradox. Remember, we need to look for some process that will take a lot of mass. So the mass loss rate of a young stars that spin fast and very active, the mass loss rate should be very high, because we need to lose 10% of mass within relatively fast time to explain the Feng-Tian sun paradox. And just to remind you again, these young active stars that rotate fast, they tend to have their activity at higher latitudes. So what if these CMEs can go from the equator or from the pole? If they go from the equator, it's an efficient mechanism, and the mass loss rate is significant. This is an efficient mechanism to take both mass loss rate and angular momentum loss. So the star will lose mass, but it will also slow down quickly. So both of these rates will be high at younger ages. But if the activity level is concentrated at higher latitudes, the CME will go out at higher latitudes as well. And as a result, this is a mechanism to lose a lot of mass, but not to lose a lot of angular momentum. So we can keep the activity level for a longer time while losing mass very fast. So this view could explain, in principle, the Feng-Tian sun paradox. And people are working to get these numbers and to see if it works in terms of the actual numbers. Okay, so that's what this states. Yeah. Okay. The final topics I would like to cover, I don't think we'll have time for the exoplanets, but you're going to hear more about it from Tron Fei, and you heard some of it from Kevin France. Flares, and this is pretty much taken from Rachel Austin's lecture from the 2014 lecture that was the basis for chapter 2 in the volume 4 textbook. Okay, so flares. And this is a nice quote that she had at the beginning of the talk. I thought it's a really nice talk. It's by Bob Lighton. He was a solar physicist in the 1960s. He was the leader of the Solar Observatory in California. A lot about what we know about the magnetic field of the sun is credited for him. The quote says that if the sun did not have magnetic field, it would be as boring a star as most astronomers think it is. And it's a quote that pretty much states the underappreciation of solar physics among astronomers. I think it's changing now, but you can still see that the sun and heliophysics is perceived by some astrophysicists as a topic that is completely understood. There's nothing new to learn there, and we just shouldn't care about it. And I think at that time it was much worse. And it's probably represent what the situation with Gene Parker when he introduced the solar wind concept. Astronomers just thought the sun must be in hydrostatic equilibrium, and that's it. So there's absolutely no way that we can introduce any process that changes that. Okay. What is a flare? A flare is a large bump in the signal. And it can be any signal. Can be specific line, can be the integrated light, can be radio signal, can be whatever, right? That's what we call a flare. A flare is a significantly increased and a quick increase in the time series we have of a specific quantity that we measure that is then dropped back to normal. So you can see this is an example of GOES X-ray. This is a hard and soft X-ray signal. You can see an X-ray flare here, another one here, another one here. In this case, the size defines how strong the X-ray flare is. Okay, so that's a flare, and it's associated with an explosion event, an event that changes the quantity of that parameter very quickly, increases its intensity, and then it drops back to normal. So it involves, in the context of stellar and solar flares, it typically involves particle acceleration, meaning the particles gain energy and different processes happens. I'm not going to read all of that. This is pretty much the first observations or report of the first observed stellar flare. It was pretty much white light observation. The first observations of flares came to be the moment we started to stare at certain signals from stars for a long time. So the signal, suddenly there's an increase. Oh, that's interesting. That's a flare. Let's try to understand what's the nature of that thing, right? So that's why flares are important. Flare, it's pretty much an unusual fast process in the ambient overall process that we try to understand, right? So on one hand, it's on top of the ambient state that we try to understand by itself, but because it's a kind of a short-lived increase, it can give us some insight about what's going on there, okay? And the more information we have, the more information we can, or the better we can interpret what's going on in terms of the actual physical process. Okay. So to start, stellar flares show many commonalities to solar flares. So we think that a lot of stellar flares are generated in a similar manner to solar flares. And of course, in the sun, we have much more details, just like we discussed before. Stellar observations are necessary to necessarily limited in completeness, just like we just stated. But again, stellar flares are much more varied comparing to solar flares. So again, it's the detailed information we have about one case versus wide range of data, sparse data that we have on many different other cases. And again, we try to relate the flare information to the physical processes that are going on. Flare is a temporary increase, again, in some parameter. And we should consider a situation where flares are so frequent that they take over the ambient state. And again, it's in the context of mass loss rates of CMEs, but also the flaring activity of a star. If you think about the ambient X-ray flux, for example, and there's a point that star has so many flares and they're so frequent that the flaring state is the ambient state. And it's important because, click here, the ambient state and the flaring state might be generated by different physical mechanisms. So it's important to identify where the ambient state becomes the flaring state. We need to look at that maybe in different tools and models. This table shows an interesting comparison between the solar and different kind of stars, flares. The energy of a typical solar flare is about 10 to the 32 ergs. For reference, the ambient X-ray flux from the sun is 10 to the 27, so flare is a significant increase in that energy. Young stars have 10 to the 36 ergs. Single stars, typical flares like that. Binary stars have much stronger flares, 10 to the 38. Gamma ray bursts have energy of about 10 to the 50 ergs. Again, unconceivable amount of energy. This is the time scales of flare. The sun is a few hours. Young stars is a day. Single stars, several days. And binary stars a week. So it's a long duration of the process that generates the flare. This time scale gives us a hint about how long that event and process actually takes. Okay? This is the percentage of the increase comparing to the ambient state. And again, you can see that there's a range here. And this is specifically for the X-ray, which is our best indicator for stellar flares. Okay. And this is the kind of stars that typically flaring. T Tauri stars that have star and magnetic field and disk that goes around. And as a result, there's a lot of interaction with the magnetic field that can generate some kind of reconnection, or call it other magical breaking of the field, acceleration of the material. This results in a flare activity, and these systems show a lot of flaring activity in general. Binary stars, again, there's an interaction between two magnetic fields, if you like, and there's a relative motion between them. So there will be a lot of dynamics that release material in an explosive manner, and this is also flaring activity. And finally, we have the very active star. This is an animation of EV-LAC, is the star that I mentioned before. It's one of the strongest flares ever observed came from this star. So there's stars, they're just single stars, but they're very active, so they flare a lot. And this shows a number of observations of different flares. I think most of it is X-ray. We also observe flares in white light. A lot of Kepler stars, for example, show a lot of flaring activity in the white light. Again, flare is just a fast increase in the intensity. So you can see different flares, and you can see they have different shapes, different time scales. Some of them go up really fast and then drop slowly. Some of them go slowly and drop slowly. You know, we probably discussed the difference between. Have you discussed, Dana, gradual and? I think Amitava might mention it later. Okay, impulsive versus gradual events. So these terms refer to the shape of the signal, how fast it goes up, how fast it drops. And there are different mechanisms that can generate one or the other. So again, it's all related to how we interpret the signal of the flare to the actual physical process that generated the flare. And this is another example. So flare can be manifested in different wavelengths. It can be manifested in radio because we have acceleration of electrons that generate radio signals. And then it can be manifested in different high energy bands like X-ray, UV, etc. Because flares are associated with plasma heating, local heating that generate this local enhancement of these emissions, and then they get back to normal as the plasma cools off. Okay, so that's what the flares does. And this is the kind of observations that are available for solar and stellar flares. You can see that the main missing link in stellar flares are the parameters that are associated with the CMEs. This is the actual mass that is being exploded to space. We can see it in the sun. We can't see it in CMEs, in stars. But many of the other observations we can also observe in stars. So in stars, we see the flares, but we don't see the CMEs. That's why it is so important to derive a scaling law that works between the flares and the CMEs, because we can extrapolate from the flares that we can see the CME information that we don't see. This is just a bunch of instruments that are used to observe flares in different wavelengths. You can see we have radio instruments, optical, UV and EUV, soft and hard X-rays. And all of them generate different signals, but there's a so-called Newport effect that all these signals seems to be timed in the same place, meaning that the trigger of the flare and the initial increase in the signal happens to all these signals at the same time. And that gives us some information about the nature of the flare. This is the general view we have on the flare, at least on the sun, but we believe the same thing happens on other stars. We have storage of energy in this magnetic loop. Some magical reconnection will trigger an increase in energy here and acceleration of particles. These particles, some of them will stream down along this flux tube and through the flanks of the CME. And through the process, they will hit these flanks, and they will hit the plasma here to certain temperatures that will emit in certain wavelengths. Then they'll hit the chromosphere and will create a hotspots here with different temperature that will create different wave bands, emissions. And also, here we're going to have acceleration of electrons that will generate radio emissions. And as the CME will go out, there will be a shock forming here that will also accelerate electrons. That will generate a different type of radio emissions. So this whole thing will generate emissions pretty much across the electromagnetic spectrum. And we can observe a significant amount of these emissions to quite high resolution in the sun, but also part of it for stars. So we have emissions that are associated with accelerated particles heating the plasma to different temperatures. Therefore, we get different emissions in different bands. And we have acceleration of electrons that will generate radio emissions in different wavebands. These are synchrotron emissions and similar processes that drive radio waves or radio emissions. Okay? So this is exactly what I say here. The emissions are a result of accelerated particles interaction with the coronal chromosphere and photosphere, and accelerated electrons. It drives radio emissions. So this is the last plot I will show. This is from Rachel Austin's paper from 2012. One of the things, it's still not clear, and people are still working very hard to construct some kind of integrated information like that, is we would like to have the frequency of flaring as a function of stellar type in general. And that means that, young active stars and their flare rate, and then as the star get older and older, They're slower in rotation. They're less active. You want to map what's the flaring activity across this range of age, rotation, activity axis. And this is something that we still don't have the full picture. But this is kind of a plot like that. This is the frequency of flares per hour in the y-axis, and this is the overall energy of the star, if you like. So it's kind of a bizarre axis, a weird axis in the context I just showed, but still, it gives us some scaling that we have high frequency here for, sorry, this is the kinetic energy of that would go to the CME, okay? So the higher this energy, the less energy we have that will go for the flare. That's what it really means. So the higher kinetic energy we have less energy goes to the flare, we have less smaller amount of flares seen here, while if the kinetic energy is lower, we have more energy available for the flare, so we have higher frequency of flares appearing on the plot. So this is where my talk ends before I move to the exoplanet. I can spend maybe 10 more minutes about the exoplanets if you like, or we can stop here. Anyone? Let's do it quickly, okay? I know your brain is, we didn't take another break, but let's do it quickly. And again, you're going to hear a lot about this later. So just planet habitability in the context of kind of what I talked now. You've probably seen this before. The standard definition of the habitable zone is traditionally defined by the distance of the planet from the star and the luminosity of the star, and that defines the surface temperature on the planet surface, the surface temperature of the planet, and if it's above freezing or it allows liquid water to exist, it means that the planet is habitable. This is an extremely simplified definition. But this plot shows the habitable zone as we move to fainter and fainter stars. This is the sun, G stars, K stars are fainter, and M stars are the most faint stars. But they still, about 70% of the stars in the universe are M-dwarf stars. And you can see that the habitable zone should be very close to the star itself, pretty much at extremely close in orbits. And we recently found some planets that orbiting M-dwarf stars in the habitable zone within that distance. And in particular, we had the TRAPPIST-1 system that I think you heard a lot about it from Kevin France. So TRAPPIST-1 is the central attention now in the exoplanet community because it's identified to be a habitable set of planets. There are 7 Earth-like planets that were discovered in the habitable zone. So here I just reviewed the alpha point. I'm just going to skip that. When the planets are really close to the star, one unique situation we're going to have is that the orbit of the planet, shown here in red, this is the background shows the equatorial plane of the stellar corona of an M-dwarf star. This is EV-LAC. And it shows the density. And this is the Alphen surface in white. You can see that for some planets, they cross this Alphen point in and out along their orbit. And this is a very fast orbit. This is 2 or 3 days orbit. So the planet crosses the Alphen surface twice, or even 4 times, within 3 days of orbit. And it's important because if the planet resides within the Alphen point, it will have a magnetosphere that looks like Io. You have this Alphen wings shape. I don't know if you talked about it or you might talk about it in future talks, but it has certain structure of the magnetosphere that kind of has 2 standing lobes that hold like that. The flow around is subalphenic, but as it reaches the superalphenic wind, these lobes are draped to the back, we have a magnetotail. We have a formation of a bow shock in the front. And this is a magnetosphere that looks like the Earth. But the point is that within 3 days, which is pretty quite short period of time, the shape of the magnetosphere is completely changed, drastically changed. And this change in the magnetic field can drive a lot of currents and deposit a lot of energy into the top of the atmosphere in the form of heating. Okay? So we can drive a lot of heating at the top of the atmosphere only due to the rotation or of the orbit of the planet around the star in this closing orbit. So this is one aspect that we need to pay attention to. Skipping that. So in general, these closing planets reside almost in the stellar corona. So the conditions of the space weather, the condition of the stellar wind that interact with this planet are extreme. First, the UV flux and X-ray flux are extremely higher, about 100 times higher or even more. The stellar wind is much more extreme, and this is in particular because the density is about 1,000 times higher than 1 AU at these orbits. So think about the dynamic pressure that's just pounding on the planet. It's 1,000 times higher or even more. Okay? And these planets reside in a coronal background plasma of 1,000,000 degrees Kelvin. Okay? And there's high ambient magnetic field as well. Also, instead of 1 nanotesla, it's about 100 or even 1,000 nanotesla. So everything is much stronger in this orbits. And because this planet resides in a subalvenic point, there might be an interaction, magnetic interaction between the planet and the star. And this will happen even if the planet doesn't have a strong magnetic field of its own. It can be direct streaming of coronal plasma onto the planet. Okay? So the question is, can these closing planets sustain an atmosphere? This is one big question, because if they cannot sustain an atmosphere, then most likely they won't be habitable. Even though planets can be habitable anywhere in the universe, we should not stick to the assumption that life in the universe should be exactly like the Earth, right? And even on the Earth, we find extremophiles. These are life forms that live in places that we did not expect them to exist. Extremely hot, extremely cold, extremely saline environments. These black smokers in the middle of the ocean, 700 degrees Kelvin and 90 atmospheric pressure, or 90 atmospheres of pressure, or I don't know the exact number, but conditions that are similar to the surface of Venus to some extent. So it might tell us that it's better to look for life on Venus than Mars, maybe. That's the point. A side note, not only we need to explain if they can sustain the atmosphere, we need to explain how to start the atmosphere in the first place. And this is something that nobody has done so far. So these are some simulations that pretty much try to quantify the conditions of the stellar wind at these orbits. You can see that this is the dynamic pressure of the wind for TRAPPIST. This is Proxima Centauri b, which is another exoplanet that was discovered, our nearest neighbor, but still an M-dwarf star. This is the dynamic pressure of the wind normalized to the dynamic pressure at 1 AU. And you can see that at times it can be maybe 20,000 times higher. And the other thing I would like to draw your attention is that the transitions from this lower dynamic pressure to high dynamic pressure are extremely fast. This takes about a few hours. So within few hours, the magnetosphere is being pushed all the way almost to the surface of the planet, and then back, and then pushed back, and so on, within a matter of hours, which is the time scale of a typical geomagnetic storm. And this is only when as the planet orbits the star. There's no transition, no CMEs here. It's just the orbital motion that drives this. This is another simulations, one of them by Tron Fidong. He will probably talk more about it. And the other one is by Keita Garcia-Sage, that they use models to try to estimate the mass loss rates of these planets. And the experiment was just taking the Earth, move it to these closed orbits, and calculate what it will do to the escape rate of ions from the atmosphere. And the escape rate can be boosted by 4 orders of magnitudes or more. Bottom line is that the atmosphere should escape much faster than in the case of the Earth. And therefore, it's a problem because these numbers show that the planets should lose all their atmosphere very quickly. They cannot sustain the atmosphere. That's the answer. And I think that's pretty much it. I have some nice movies to show, but I think we can stop here. Okay, so I'm just going to wrap up the whole thing. We talked about solar versus stellar physics, in particular in the context of the available observations. We talked about stellar evolution. And we talk about how corona winds and astrospheres can potentially change with the range of parameters that we have across the different spectral types. And we focus on solar analog slow mass stars with hot corona. And we also talk about how winds and across the different spectral type can affect the stellar evolution in the context of magnetized winds and their effect on stellar mass loss rates and spin down rates. And we talk about solar and stellar flares. And we finish with exoplanets bit. Okay, so that's where I stop. Thank you, and I'll be happy to see if you have any questions. Questions? Each one of you should have at least one. This is a 3 hours lecture, so at least one. Yeah.
Are there attempts to make or predict the flare or flare effects on the laboratory experiments?
You mean the observations?
For example, have they tried to make a setup so that they can produce some flare on some laboratory?
Yeah, there are experiments. These are nuclear laboratory experiments that involve plasma physics. There's Paul Bellin group from Caltech, I think. They try to produce coronal loops in the laboratory. You all know that plasma doesn't like to stick around in a controlled manner. So I think they did get some instabilities driven that they could associate it with flaring activity. But I think the main thing is the scaling of the energy. You need to store a lot of energy and then have the sudden release. And I don't know if any laboratory experiment can generate such a high energy in this manner, at least. Well, we all know, you should know by now, that we call space physics, space is the natural laboratory for plasma physics. And one of the reasons is that the conditions in space and the parameters that we have in space are ones that are extremely even impossible to do in the laboratory. So we count on the natural processes to be our, to some extent, our controlled experiment. Because this is the only way we can actually observe plasma in such conditions. Okay. Any other questions? Yeah.
Are there any Fermi lab observations of flares in other stars?
These are the extremely high energy particles. So we do see solar gamma rays that are associated with the flare, and there's some mechanisms to explain them. I mentioned at the beginning this new set of gamma rays, solar gamma rays, that they have 10 to over 100 GeV energy, and these cannot be explained with the flare. There's just not enough energy in the flare to generate them. What we think is that these particles are generated by 1 TeV cosmic rays that penetrate all the way to the solar surface and interact with the actual, even subsurface of the sun, and by some process generate gamma rays that then go out. But this is a completely new thing. Pretty cool stuff. Yeah. Any other questions?
What kind of observations? You were talking about this set of Earths that could be inhabitable. So what kind of evidence?
Well, what they do, the reason the exoplanet community was pushing for the search of habitable planets around M dwarfs is that first, these are the most common stars in the universe, about 70%. But also because the habitable zone is so close, these are the only planets we can actually observe. Because there's an observational bias that you can only observe planets that are really close. Imagine that this is your star. You observe the light that is coming from here. The planet is tiny. So only if the planet is really close, you can actually see its effect blocking some of this light. If the planet is far away, you won't see any effect on the signal. So you're biased to only observe very close planets. So there was this strong push to search for Earth-sized planets around M dwarfs because these are the only ones that could be observed and can be in the habitable zone by this simplified definition. The problem is that after we found them and identified them, we realized that they might be too close, so maybe after all they won't be habitable because the habitability definition must be extended beyond this. For example, taking into account space weather effects and the extreme space and stellar environment at these close orbits. Yeah.
Follow up on that question. Are there any observational techniques just how you show that you see the stellar heliospheric shockwave or
Yeah.
something like for a star? Are there like similar ways to find out like whether an exoplanet has a magnetic field?
So one of the ways that people looked into we didn't detect any magnetic fields of the planets yet. The ways people have tried to look into that is to look for some kind of interaction that is associated with some kind of flaring activity. For example, people looked at a scenario that the star has a certain field and the planet is orbiting around with different field. At some point you have reconnection that streams back accelerated particles back to the chromosphere and locally hit them. So people look at calcium line, which is associated with the chromospheric temperature. And they thought they seen small increase, tiny increase, that they think they could associate with the planetary motion around. And this is what started the so-called star-planet interaction niche. Some people have tried to look at this effect in the X-ray. They couldn't really get anything conclusive. So there's an attempt to indirectly deduct whether the planet has a magnetic field or not. But even these chromospheric emissions are still under debate, and they're not conclusive. But there's a series of papers. The effort was led by Evgenia Shkolnik, so you can look for her paper, and I'll be happy to send you some references. But the idea was to look at this chromospheric line and identify a small BAP that is repeating and is repeating with time scale that can be associated with the orbital time of the planet that we knew that is there. So that's one thing. We knew that there is a planet there. We knew the orbital period of that planet. So that's what they tried to do. Yeah.
Can you explain the angular momentum loss to torque?
Well, again, the idea is that you have these magnetic field lines that extend to infinity, but they're still connected in one end to the star. The star rotates, but these field lines are kind of held fixed at at infinity. So what will happen is that it's like a rope that is held on the star, and as the star tries to spin down, this rope slows it down. So that's kind of and it applies through a torque application on the star. But this is kind of the most intuitive analogy that I can think of. That the magnetic field is kind of a rope that you hold the star and you spin it down. And if you do it this spin down, by the way, this spin down mechanism, the magnetic braking mechanism, works only on a long time scale. We're talking about evolutionary time scales. The effect is tiny if you think about in the context of solar time scales, like the current sun time scale. Only the integrated effect, or the integrated effect becomes notable and important only if you're talking about the long time that you apply this torque on. If you only account for 100 years, it's nothing. Yeah?
In terms of these highly active stars with the activity more towards the poles at like higher latitudes, observationally maybe there's not anything, but theoretically, what would be the impact on like stellar cycle, like Joy's law, or do we see preferential polarities in different hemispheres?
We don't see. This is first. It's nothing that we can actually observe. Even these observations are, well, there are observations. This is the only thing we have, but there's still a lot of uncertainty going not to the observation itself. The observation itself is just the polarization of the light. That's a definite observation. It's the interpretation that we take from that observation that is uncertain and iffy. So that's where people are still not sure, is that good enough to really say this is what's going on or not? Well, the theoretical aspect is dynamo theory, and I also already stated my view on dynamo theory. I mean, I think people like Carl Schreiber, Carl Schreiber ran a model to explain that, and they did get some transfer of concentration of flux in the polar region. But that was a flux transport model. So it's just 2D model of the flux on the surface. It didn't account for the full dynamo everywhere, like the 3D dynamo. And one of the biggest disconnects I think we have in the context of dynamo theory is that we see manifestation of the magnetic field on the surface of the sun. We have a lot of information about it. Things you just stated, Hale's law, meridional flows on the surface are observable. We can track features over a long time to deduct some kind of repeating behavior that we see on the surface. The problem is that it seems that there's some disconnect between what we see outside and what happens inside. And I think that's one of the reasons why dynamo models are still have issues to really explain what we see, because it is possible that even few layers below, things happen in a completely different manner that we don't know. And this disconnect between what we see that serves as our constraint and what might happen inside doesn't match to the theoretical description we try to solve for. And that's one of the main reasons why dynamo models still have problems to explain the physics. Because we see one thing, maybe there's another thing going on inside that we don't know about. Yeah. So we actually see superflares, and this is a recent call by the Living with a Star program, was about the solar-stellar connection. And one of the topics that they try to resolve in that call is that to develop explanations, how come we have superflares in sun-like stars? We actually do have few examples. You see G stars like the sun, they have superflares. They have flare with such energy that it's really hard to come up with a model. How come the sun produced such high energy in the form of a flare? Okay? So in general, physical processes that we try to understand, we assume we have a certain amount of energy available to produce a process that we see. In the case of super flares, the problem is that the flare is so intense that it produces too much energy or more energy that we think the sun actually has to produce it. So where does this energy come from, right? So flares from sun-like stars is a completely open question. Oops. So we don't know. Any other questions? Okay, are we done?
Okay.